Hello class and welcome to 6.6 exponential and logarithmic functions. I appreciate you watching this video. So in this examples or in this part of the notes, we're going to talk about how to solve exponential equations. And we're going to begin by first using what's referred to as a one-to-one property to exponents, which states that if we have two powers, two exponential values, so you see right here, we have a power here of b to the power of m, and it equals to a power, again, of the exact same base, then that means that the exponents are going to equal to each other. So the way we're going to solve these, at least the first part of today's equations, is that we're going to make sure that we have two equivalent powers so we can set the exponents equal to each other and then solve for the variable. So the simplest situation is that it's already done for us, like in example 1a. Here we have the exponential equation, or the power here, of 7 to the power of x plus 3, and it equals to a power of the same base, the power of 7 to, or the power of base 7 to the 2x minus 7. This is, again, the easiest thing that could occur in these type of exponential equations, that it's already set up that the powers have the exact same base. So I can, again, determine the value of this thing by equaling to those two things, equaling these values equal to, the exponents equal to each other. There I go. I was having trouble saying that. So all I have to do here, since these two bases of these powers are the same, then that means that the exponents are equal to each other. So x, don't like the thickness of that, x plus 3 equals 2x plus 7. So all we're going to do now is simply solve this equation by, in this case, because it's a linear equation, x to the first power and x to the first power linear equation, we're going to do letters to the left, numbers to the right. So I'm going to move this to this side, and I'm going to move the 3 to this side. So I'm going to have a positive 1x, and since I'm moving the 2 to the other side, that's going to become the opposite, negative 2x. And now I'm going to do, on the right side, I have a positive 7 already there, but I have to move this positive 3 to the opposite side of the equation, so that's going to change it to a negative 3. Then combining the like terms, this is going to be negative 1x. This will be a total of 4. And dividing by 1, negative 1, x equals negative 4. So there is your solution to the first equation. So let's now move on to the second example. So for this example, same scenario. We have two powers and the bases are the same. Here the power has a base of 3 and the exponent is 5x plus 4. And that's going to equal to a power where the base is also 3, but the exponent is 8x minus 11. Now, since those bases are the same, that means that the exponents have to equal. So we're simply going to get our 5x plus 4 and set it equal to 8x minus 11. And now we just simply follow our algebra rules to solve this equation with letters to the left, numbers to the right. So transposing these two terms, we have a positive 5x minus 8x. And then on the right side of the equation, we have a negative 11 and now a minus 4. So simplifying the left side, 5 minus 8, that's a negative 3. And negative 11 minus 4 is negative 15. We'll divide by negative 3. And our value of x is positive 5. And there you have your solution to this exponential equation. Now, in this situation is a more complicated scenario. Here we do not have our powers, or at least it doesn't look like we have an exponential equation of powers with the same base. But if we pay close attention to 81, well, 81 is a result of multiplying a specific number of 3's. So if it's a possible way of changing this right here, we can use this one-to-one property. I just have to manipulate this number here, so it's a result of raising the base 3 to a specific power to get 81. So it'll be up to us to be able to recognize this type of situation. So even though it looks like we don't have a power equal to another power of the same basis, our objective here is to first manipulate this 81 so it's a power with base 3. And our hint kind of gives it away. So we're going to try again because this is a power of base 3. That's going to be our hint to try any power of 3 or 3 to any power. Well, we know that 3 to the second power is equal to 9. 3 to the to the third power will simply be 9 times another 3, which is 27. 3 to the fourth power would be the previous answer of 27 times another 3, which is in fact equal to 81. So 3 to the fourth power does in fact equal to 81. So we can manipulate this and write the right side of the equation as a result of 3 to the fourth power. And look at that. By doing exactly that, we have an exponential equation. We have a power on the right side with a base of 3, and now we have a power on the right side, with base of 3. I meant to the left over here. So, because the powers have the same base, that means that the exponents have to be equal to each other. So we can now simply ignore the bases and get 3x minus 8 and set it equal to 4. So to solve this equation, again, letters to the left, numbers to the right, that means we're going to only simply move this 8 to this side. So plus 8. So we end up with 3x equals 12. And dividing by 3, x equals to the answer of 4. So moving to this example, similar situation here. We have a power on the left side. Our base is 4, but there's no power on the right side of base 4. So since this is a power of base 4, let's see if we can manipulate this so we can write this as 4 to a power. So 4 to the second is equal to 16. 4 to the third will be 16 times another 4, which is 64. 4 to the fourth power will be 64 times another 4, which I believe is 76. Let me do the math real quick. Oh no, it's way off. It's 256 already. So 64 times another 4 is 256. So there you go. So I can change this number here to 4 to the fourth power. And since I already have the power on the left side of base 4, that means that these exponents are equivalent. So 2x minus 8 equals 4. And then solving the equation with letters to the left, numbers to the right, we're going to get 2x equals plus 8 over here. 12, and then dividing by 2, we get that the value of x is 6. So there's your solution to this equation. Let's now look at this example E. Now, if we have a situation where we have power and instead of getting a whole number, like right here, we have a number under the value of 1, then this is your hint again that we can still manipulate this so we can write it as a power of base 5. But however, our exponent is just going to be a negative number. So remember, let me write this down here, that if I have 1 over a base with a positive exponent, that is the exact same thing as flipping this, putting this above 1, so x over 1, and that changes the exponent to the opposite of whatever it currently is. So if I start off by first focusing, what does 5 to the second power equal to? A positive 5 to the second power, that's equal to 25. So that would mean that if I have 5 to the negative 2 power, that's simply going to be 1 over 25. Similarly, 5 to the third power, that's 125. And 25 times another 5 is that. So that means that 5 to the negative 3 will be 1 over 125. So using this here, this one specifically, I can rewrite that number there as 5 to the negative third power. So that's going to equal to 5 to the 3x plus 6. And then I can apply the same property as before. So the exponent is going to equal to that. So this 3x plus 6 equals negative 3. And with letters to the left, numbers to the right, I'm going to move this 6 to the other side, making it negative 6. 3x will equal negative 9. Dividing by a positive 3. X equals negative 3 as a result. So there is your solution. So continuing something similar to the previous example, here We have 1 over 64. And we want to check again, since on this side of the equation we have a power of base 2, we want to check if we can write this as a power of base 2. So let's start first again with positive exponents. So if I have 2 to the second power, that's equal to 4, which means 2 to the negative 2 would be simply the reciprocal of that, 1 over 4. 2 to the third, that's 4 times another 2, which is 8. So 2 to the negative 3 is 1 over 8, and so on, okay? So I'm not going to do any more of these over here until I get the number that I want, which is 64. Because I just want to put it underneath the 1, so I just need to get the negative exponent of whatever gives me 64 when I raise 2 to a power. So 2 to the third is 8. 2 to the fourth will multiply another 2, so 8 times 2 is 16. 2 to the fifth will multiply 16 with another 2, so that's 32. And 2 to the sixth will multiply 32 with another 2, which is 64. So this is the one that I'm going to use. So if 2 to the 6th power is equal to 64, by putting a negative 6 there, that's going to give me the 1 over 64 that I want. So I can replace that with this value of 2 to the negative 6. So now that I have that, I can now solve by getting the exponents equal to each other. So we're going to move the 26 to the other side, making it positive 26. So 4x equals 20. We're going to divide by 4, and our solution is 5. So let's now look at this next example. So here it looks almost like the first two examples that we did, A and B, but the only difference is that the bases to these powers are not the same. And if I look at the smaller base here, 4, I cannot multiply 4 by itself an n number of times to get 8, nor vice versa. 8 cannot be converted into to 4 if I get rational exponents. Now, in these type of situations, the best strategy is to always look at the smaller base when they're not the same and see if you can manipulate the smaller base to equal to the larger base. And again, we can't, like I mentioned earlier. So 4 to the second power, that's equal automatically to 16, which is already bigger than that number there. So that means I would have to raise 4 to a decimal value, and that decimal value is going to be hard to determine to get that specific value of 8. So what do? Well, what we do is that we look for a smaller base, a base smaller than 8 and 4 that can be raised to a power to give you both 8 and 4. And if we look at the prior examples, I think there is one that does that. We actually just listed in the previous one, 2. Right here, 2 to the second and 2 to the third. 2 to the second gives me 4, and 2 to the third gives me 8. So I can do those manipulations and change these bases using that notation. So for 4, I can replace 4 with 2 to the second power, and I can replace 8 with 2 to the third. So let's do exactly that. So here I'm going to write 8 as 2 to the third power, and I'm going to put it in parentheses because that's going to be raised to this exponent of x plus 2. And I'm going to now replace the 4 with 2 to the second power in parentheses and raise that to the 2x minus 3. Okay? Well, let me remind you of another important property here that we haven't discussed in any of these sections in this module, is our power of power property from Algebra 1. That if I have a power, okay, so x to the power of n, but that's also being raised to another power, let's say m, this gets simplified by multiplying the exponents together, m times n. So for example, if 2, I'll use, we'll do 2. We'll do 2. 2 to the third power, which is 8, and that's raised to the second power. Let me not use 2. Let's use 4. if 2 is raised to the second power, which is equal to 16, and then that 16 is raised to the third power, that's the exact same thing as raising 4 to the 6th power. 2 times 3 is 6, so 4 to the 6th power. So let's verify that. So let's verify that again, which I mentioned. Okay, so we have 4. We're going to start by raising that to the second power, which, like I mentioned, is 16, and then raising that to the third power, which is a total of 4,096. But if I raise 4 simply to the 6th power, that gives me the equivalent value of 4,096. And so as you see, by multiplying the 2 and the 3, that which is 6, I can also use that as the exponent. So these two things are equal to each other. Therefore, since multiplying those exponents is the way we simplify it, we can do the exact same thing here, and we can multiply this together, and we can multiply this power with that exponent right there. So that would mean that's 2 raised to the 3x plus 6 equals to 2 raised to the 4x minus 3. So all I did was distribute and multiply both of those values with that new exponent of 2, and this I multiplied both of those current exponent of x plus 2 with the new exponent of 3. And now I can follow the same technique as before. Because I have powers with the same base, the exponents are equal. And now we just follow our simple rules of letters to the left, numbers to the right. So I'm going to move this to this side, making it -4. I'm going to move the 6 to this side, making it -6. And I have 3x minus 4x equals a -3 minus 6. So combining the like terms on the left, that's -1x. Combining the like terms on the right, that's -9. And dividing by -1, we get our solution of +9. So the solution to this equation is x equals +9. Moving on to the last example on this front page, same scenario, same situation as the previous example. This and this power do not have the same basis, and 9 cannot be raised to a power to give you 27, and vice versa. So what we're going to do is look for a number smaller than both 9 and 3 that can be raised to give us both of those numbers. So let's start off with 9. Let's see if we can find a number that can give us 9. So we know 2 wouldn't work, because again, we just did those. On this example up here, we have them listed there. And I think we have 3 somewhere here. Yeah, look, 3 right here. 3 to the second is 9, 3 to the third is 27, and 3 to the 4th power is 81. So we already found one, since we already did it earlier. Use that example there. So no reason to rediscover this. We just know that 3 will work. So I can write 9 as 3 to the second, and 27 as 3 to the third. So again, just to recap. So if you can't write this as a power, raising this to a power to get this number, or vice versa, get the larger one and write it to a power to get the smaller number, then find a smaller value that can be raised to a power to get both. So right here, that number would be 3. So 3 to the second and 3 to the third. So let's replace 9 with 3 to the second. And again, we're going to put that in parentheses and write the current exponent. 27 is going to be written as 3 to the third in parentheses and raised to the x minus 1 power. And just like before, because we have a power of power, we can multiply these exponents together. So we're going to multiply both of these two terms by 2. And we're going to multiply the exponent of x minus 1 with 3. So distribute 3 to both of those terms. So 3 is raised to the 4x plus 10. And the 3 on the right side is going to be raised to the 3x minus 3. So now we can get the exponents equal to each other. So 4x plus 10 equals 3x minus 3. And if you want, you could do the distribution after you set up the equation. So you don't have to distribute first. You could also do this. Already ignore the 3's and just understand that these things get multiplied. So you have 2 times 2x plus 5 equals 3 times x minus 1. So distributing, again, is going to give you this. And when I distribute the 3, I still end up with the exact same thing on the right. So now solving the equation by letters to the left, numbers to the right, we're going to move the 3 to this side, making it negative. We're going to move the 10 to this side, also making it negative. And we end up with 4x minus 3x equals a negative 3, bringing the negative 3 down, and the 10 to the other side makes it negative 10. So 1x equals negative 13. And since we're going to divide by positive 1, that's not going to change the value of negative 13. So there is your solution to this equation. All right, now let's say that this doesn't work, that there is no way to get our bases to be equal on these powers. So I have a power of 3, we'll do something 3 to the x plus 4, and that's going to equal to a power of 2 times x plus 7. So there's no way to get these powers to have the exact same base. Well, in those situations, when we can't do that, we have to apply a different property. So if you'll turn the page, let me explain what we do in those type of scenarios. So as I was mentioning, if this one-to-one ratio doesn't work, where we can use that one-to-one property of exponential solving equations, then we're going to use logarithms in those scenarios there. So we have to first make sure, again, like with the exponential situation, like in the previous examples, that we have isolated the exponential expression. So we want, again, the power to be the only thing on the left side or on the right side of the equation, and it to equal to a constant. So we want it to look in this format of some base raised to a power of x, and it's going to equal to a constant. So we have to do any inverse operation to get that format there. Now we're going to use the logarithmic function with the same base as this power. So depending on what power we have here, what the base of the power is, will determine which log function we use. If it's e, if our base is e, then we're going to use the natural log, and simplifying one of the following properties is going to be true. If it's a base 10, so if it's 10 to the power of x, then we're going to use the common log. But if it's any other power, with any other base, in this power, then we're going to use the appropriate log that corresponds to that power. So we can apply this property here and cancel out the base of the power and leave us only the exponent of x. We're going to solve for the variable, and then we're going to use a change of base formula if necessary, which is specifically necessary to this one. Okay, so if I have that my solution is that x is going to equal to a log base b of some value y, we'll call it y, then using the change of base property, I would write this as I'm going to use the natural log, not the common log. The natural log of y divided by the natural log of b. And again, all of this will make a lot more sense when we look at actual examples, explicit examples to, again, this procedure here. So let's look at example 2a and see how this applies. These steps and these rules apply to that first equation, that first example there. So for this example right here, first thing I'm going to do is get rid of, again, any vertical dilations, any vertical stretches. So anything that I'm adding or subtracting to my power. So first of all, I have to recognize my power, which is 10 to the x power. So I want this isolated. I want that to be the only thing on the right side, in this case, the left side of this equal sign. So I basically want to do letters to the left, numbers to the right, but with power. So I want my powers on the left and everything on the right side. So I'm going to move this number 8 to that side, making it negative 8. So it's going to cancel out. So 10 to the x power equals to a total of 120. Okay. Now, this is what I was referring to on the previous page. What happens if I can't raise 10 to a power to get 120, or manipulate 120, write 120 as a way of base 10, as a power of base 10? And like in this example, I can't, because 10 to the first power is equal to 10, but 10 to the second power is equal to 100. But then when I go to 10 to the third power, it jumps all the way to 1,000. So there's no way that I can write 120 as a power of 10 to an exponent that's going to be a whole number. It's going to just be some type of decimal. And to guess what that decimal is going to be relatively difficult to do. So I don't want to do that. I'm only guessing again what power I need to raise 10 decimal value to get 120. It's possible, but I don't want to struggle and go through that whole process. So instead, we're going to use logs in these type of scenarios. So because this is a log of base 10, the log that I'm going to use is log base 10, the common log. So I'm going to take the common log of both sides. Because if I do that to this side, I also have to do it to the right side. So my answer is going to be this. And again, well, I'm not done with the answer, but because of this property again, the basic properties of logs, that if I have log base 10 of 10 to the x, my solution is simply going to be x. So this basically cancels out, and the only thing I'm going to be left with is the variable x. So x is equal to the log base 10 of 120. So that right there is going to be your answer. Now, you can plug this into Desmos, and because Desmos has the ability of evaluating the common log of 10, this right here is your answer. And the approximated value of this, let me get Desmos out. The common log of 120 is 2.079. So approximately 2.079. Now I don't want the decimal value of our answer, I want the exact answer. So on your homework, simply write this, that your answer is going to be the common log of 120. So let's look at this example now. So this example, same scenario. Let's first identify the power. So our power is e to the power of x. And that's what we want on the left side of the equation. So again, kind of like letters to the left, numbers to the right. We want everything else to be moved to the right side. So we'll start by moving the 9 to the opposite side, making it positive 9. So we have e to the x power is equal, that's going to end up equaling to 17. Now obviously 17 cannot be repurposed or rewritten as a power of base e, because again we're going to come across the same situation as before. We're going to end up with a decimal value and guessing that decimal value of e to get 17. Remember, e is 2.71 as it is, and to get 17, that's going to be again too much work. It's going to be too much of a headache to try to determine what the irrational value is to get exactly 17. So instead we're going to use logs. So to use a log here, because this is a power of base e, we're going to use the log of base e, which is the natural log. So if I take the natural log of the left side, take the natural log of the right side, this again is going to cancel out as stated right here in the example in our notes. Again, that property from the previous lesson. So x is equal to the natural log of 17. And to determine what the actual decimal value of this is, we can plug it into Desmos and get an approximation to the decimal value. So as you see here, the natural log of 17 would be 2.83321344406. So you see, that would have been a headache to try to determine just by guessing what that exponent was. So 2.8 gets me close to 17, but not exactly. 33 again gets me even closer. The 21 gets me even closer. The 33 even closer. Then the 4406, that gives me again 17, but as you see, it's a little bit above that because again, this is an approximation. So if I do 5, maybe it gets me closer. But there you see, as you see, as what I'm trying to get to, the point I'm trying to get to is that again, it's an irrational value. So there's no way to actually be 100% accurate with the appropriate decimal for the scenario. So we're going to simply write the natural log of 17 as our answer. So our answer is the natural log of 17. So let me box that in. And let's move on to the next example. So for this example here, let's highlight again our power. Our power is 5 to the power of x. And on this one, we can't just move the 2 to the other side because we're not adding or subtracting it. So to transpose multiplication, because this is multiplication now, to transpose that, we're going to divide. So to move to the 2 to the other side, that will require us to not to get the opposite of 2, but get the reciprocal of 2. So we're going to divide both sides by 2. So 5 to the power of x, well, 36 divided by 2, I believe that's a total of 18. And now we can solve. So in this example here, because our power is a base 5, the log that we're going to use is a log, is either, we have two options. We can use the log base 5 or we can use the natural log. I'm sorry, yeah, the natural log. I'm going to use the log base 5. It just makes it easier, and then I'll just simplify the solution later by using the change of base property. So here, I'm going to take the log base 5 of 5 to the x power, take the log base 5 of 18. So this and this cancels out, and x is going to be the only thing that's left. And now I have the log base 5 of 18. So now, because, well, before we're not able to evaluate this, we're going to use the change of base property. Recall that if I have a log base b of some value m, that's the same thing as using natural logs, the natural log of m divided by the natural log of b. So I did, like I told you, so this property does come in use, and it's useful in this scenario. So here we're going to write our answer as the natural log of 18 divided by the natural log of 5 instead of this notation. So this is how I want you to write your answer. Now this is still equivalent, okay? This is still correct, but on the homework I want you to write your answer like that and apply this property right here just as a way of remembering how that property works. The one thing I do not want is, again, the decimal value. Don't go into decimals and start plugging this into decimals and give me a decimal approximation of this. So for example, D, similar situation, we have a power, but instead of adding or subtracting something to our power, we're multiplying it. So to move the 3 to the other side, we're not going to do the opposite of the number. We're going to get the reciprocal of that number. So we're going to divide by 3. So 2 to the x is 7. And we're going to use, I like using again the base of the, with the appropriate base there instead of the natural log. But then, like I mentioned on the previous example, I then just use the change of base property to write that with natural logs. So here, I would take the log base 2 of 2 to the x, log base 2 of 7. And again, by doing that, this step over here becomes a lot quicker because this cancels out automatically, leaving us only with x. So x is equal to the log base 2 of 7, which now applying the change of base property means that this is equal to the natural log of 7 divided by the natural log of 2. So I like using that instead. Now you could use the natural log, so 2 to the x is equal to 7. I can take the natural log of 2 to the x power and do the same thing with 7. And using the power property, which remember is that if I have a log base b of some value of m and it's raised to a power, I can pull that exponent and multiply the log with that exponent instead. So that would mean I can pull this to the front and multiply x times the natural log of 2, equal it to the natural log of 7, and then dividing by the natural log of 2. This reduces and it isolates my variable, and x equals to the natural log of 7 divided by the natural log of 2. So you see I get the exact same answer, okay? But I prefer doing this than using this property up there. I just find it a little bit more straightforward, I guess. and easier to navigate than this over here on the right side. All right, so let's move on to the next example. So for this example, we'll begin by first identifying our power. So this is e to the power of x. And again, we want everything to be moved, first of all, to the right side. So we need to get rid of the 6 and we need to get rid of the 8. So we'll start first again with the 8, like we did in the previous two examples. So we're going to start by moving the 8 to the other side. So to move the 8 to the other side, that's going to make a negative 8 on the right side. So we have 6 times e to the power of x, and 32 minus 8, that's a total of 24. Now we can apply the property, the step that we did in the previous two examples and move the 6 to the other side by getting the reciprocal of it and dividing. So we're going to divide by 6, and e to the power of x equals, well, that's what, 4, okay? Now, because this is the natural log, we're going to use the log base e which is ln. I'm sorry, since this is a natural exponential function, we're going to use the log of base e, which is ln, which is the natural log. So we're going to do the natural log of the right and the left, of the left side and the right side. The left side is going to cancel out, leaving us only with x, and the right side is the natural log of 4. And on this one, we don't have to do any extra steps and not have to apply the change of base property. So, okay, so similar situation here. Our power is 4 to the x power. So that means we need to get rid of the 7 and the negative 11. Starting off with the negative 11, moving the 11 to the other side is going to change it to the opposite. So positive 11 will bring down the 7 times 4 to the x power. There's going to be a total of 63. Now we can get rid of the 7 by, instead of moving it and making it the opposite, we're going to move it to the other side by dividing it, by getting the reciprocal of it. So we're going to divide by 7. So 4 to the x equals 9. So now with this, we're now going to just use the log base 4, since this is a power of base 4. So log base 4 of 4x equals log base 4 of 9. I'm going to continue over here. This is going to reduce itself out, leaving us only with the exponent of x. And that's going to equal to the log base 4 of 9. And then using the change of base property, we can write this as the natural log of 9 divided by the natural log of 4. So there is your answer. So let's now So in this particular example, you'll notice that our exponential is already isolated, okay? So here we are, our exponential, our e to the power of 2x minus 3, so base e, and it equals to 13. So what we're going to do here in order to solve this exponential equation is we're going to automatically get rid of the e by using the natural log. So if I take the natural log of e to the 2x minus 4 and do the same thing on the right side, take the natural log of 13, I simplify the left by canceling these two out and getting 2x minus 4 equals the natural log of 13. Now, from right here, I can now solve. Again, I want to solve for the variable x. So I need to get rid of these two values there by doing inverse operation. So I'm going to add 4 to both sides. So I'm going to move the 4 to the other side, in other words, making it positive 4. So now 2x equals the natural log of 13 plus 4. Now pay very close attention to this. This, again, cannot be added together. The natural log of 13 plus 4 is not the same thing as the natural log of 17. I cannot add those two quantities together. And just to show you again, ln of 13 is already 2.56. If all I do is add 4 to it, notice that that number just simply increases by 4. So from 2.56, it increases to 6.56, an increase of 4 units. Notice that that is not the same thing as getting the natural log of 17. 13 plus 4, 17. Notice that those two values are not the same, okay? So if this doesn't work here, it won't work with any situation, whether you're adding or subtracting, multiplying even, or dividing. So if I'm doing any type of operations after taking the natural log of 13, that again is its own number, and adding or subtracting or doing any other operations is going to increase, decrease to all those values to that number of 2.56. So you see 2.56 plus 4 more, okay? So it increases the entire value by 4. So do not add them, do not subtract them. Now, to get the final solution here, since we're going to solving the equation for x, and we're multiplying our x now by 2, the inverse operation would be to divide by 2. So our answer is that x equals to the natural log of 13 plus an additional more, all divided by 2. So there is your response. And for this example, similar situation, since this power is already isolated on the left side of our equation, we can't move anything, we don't have to move anything to the left from that side there, and I can automatically start using the appropriate log. And again, since the power is a power of base e, I'm going to use the log base e, which again is the natural log. So 5x plus 7 will be the only thing on the left side, and the natural log of 9 will be there. So we'll start by moving the 7 to the other side, so plus 7. 5x equals to the natural log of 9 plus 7 more, and now we can divide by 5. And x equals the natural log of 9 plus 7 divided by 5. So there is your solution. Now this concludes the first part of this section here. And I hope again that this video was helpful. But if you are still struggling with these examples, check out again the help videos on the homework problems. See if those examples or those explanations are a little bit easier to follow. Or if not, again, email me through, send me a message through email on message the instructor on your homework on My Open Math, or send me a message on Parent Square on anything again that you're still not clear about. Now I appreciate you watching, whether that's again getting ahead, when you're watching because you want to get ahead, or you were absent and they're just trying to catch up. I do appreciate you spending your time and watching this video. And like always, I hope you have a great day. Goodbye.